Hello, I'm Richard with EV4U. In this video, I will be referring to our last video. So if you've not watched it, you may want to go check it out. In our last video, we discussed solar panels and how to size the solar array. In this video, we'll discuss how to get the power from the solar panels to the battery pack, from the wiring to the solar charge controller. So what is a solar charge controller and why do we need one? In simple terms, a solar charge controller regulates the voltage and current from the solar panels to the battery pack. There are two main types of solar charge controllers: PWM, volts with modulation, and MPPT, maximum power point tracking. PWM controllers use a transistor switch that rapidly opens and closes as needed to regulate the charge current going into the battery. PWM controllers don't modulate the voltage. They pull the output voltage of the solar panel down to match the battery voltage. Let's look at an example. A 250 watt solar panel may have a maximum power voltage of 32 volts and a maximum power current of 7.8 amps, and 32 volts times 7.8 amps is your 250 watt. With the PWM controller, your panel will still produce 7.8 amps, but the voltage will drop to match the battery, in this case 12 volt. That means your panel is only providing 94 watts instead of 250. 12 volts times 7.8 amps is 94 watts. PWM controllers typically are not available over 60 amps. They have a greater efficiency loss when the batteries are at a low voltage, and while it's technically possible to use a PWM controller with lithium batteries, it's not recommended due to the limitations of PWM controllers in managing charging profiles of lithium batteries. Also, the average PWM charge controller will only have 75 to 80% efficiency because of the simplified way the charging function is designed. A typical MPPT, maximum power point tracking solar charge controller, has an efficiency ranging from around 93 to 97%, meaning it can convert a large majority of the power received from the solar panels into usable energy for battery charging. However, MPPT controllers are generally more expensive than PWM controllers, but I think they're by far worth it. MPPT controllers are better suited for large solar systems with multiple panels or high voltage panels. They are more efficient and can produce up to 25% more charging than PWM controllers in cool conditions. MPPT controllers can also operate with higher voltages and lower array currents, which means smaller wire sizes. MPPT controllers regulate charge current into the battery like a PWM controller. However, they also convert the voltage coming out of the panel to match what the battery needs. Let's look at an example of how this drastically improves efficiency. Using the same 250 watt panel, the MPPT controller allows the panel to operate at the maximum power voltage. Now, the power going into the controller is the full rated 250 watts. The output from the controller to the battery still needs to match the 12 volts, but the current increases to 20.8 amps, allowing you to utilize the full 250 watt potential of the panel. So 12 volts times 20.8 amps, that's your 250 watts. This is why I recommend using an MPPT controller. Solar charge controllers have voltage and current limitations, which is why you need to match your solar charge controller to both the solar array and the battery pack. The first limitation we'll look at is the maximum input voltage. A high quality solar charge controller may have a maximum input voltage of 250 volts, where others may be limited to 100 to 150 volts. Let's look at an example of a solar charge controller. Here's some rating. Nominal voltage is either 12, 24, 36, or 48 volts, and they'll have auto recognition. Once you hook up the battery, they know what your battery pack nominal voltage is. Common is a 60 amp rating. They'll have a 20 amp load current, and I'm not going to be talking about those in this video. And they'll have a maximum solar array input power of 800 watts at 12 volts, 1600 watts at 24, 2400 watts at 36 volts, and 3200 watts at 48 volts, and maximum solar array input voltage of 140 volts DC. And then they have a self-consumption rate, which means that they're going to consume some power just to operate the internal electronic. And then they give you the terminal sizes and what gauge wire it'll accept. And then here's an example of a 400 watt solar panel spec sheet. It gives you the dimensions, the weight, the maximum power, 400 watts in this case, maximum power voltage, 30.9 volts, maximum power current, 12.9 amp, and the open circuit voltage, which is, if you just check the output with a voltmeter, read 37.1, short circuit current, 13.7 amp, and a maximum system voltage, if you had a bunch of these in series, would be 1500 volts. For the sake of this discussion, let's assume 140 volt maximum solar charge controller input voltage, as in the example we just looked at. Looking at 400 watt solar panels, as we discussed in the previous video when we were designing our solar array, we see that we have a maximum output voltage of 37.1 volts. Based on this information, we can place 4 panels in series. 37.1 volts times 4, that's 148 volts. volt, which slightly exceeds that 400 volt maximum. But remember, that 37.1 volt was open circuit. So when you put them in series and there's a load, they'll be below that 140 volt threshold. Anyway, that makes this 8-panel option more appealing. Remember, we discussed and compared 3 setups in our previous video. We compared a 6-panel setup with an 8-panel and 10-panel setup. The 8-panel array would have 2 4-panel series strings. There's also other panel size options from 100 watts to 550 watts being common sizes. Now let's examine the current limitations of the solar charge controller. MPPT solar charge controllers typically specify the maximum watt at either 12, 24, 36, or 48 volts, like we looked at a minute ago. A common solar charge controller, 60 amps, is rated at 3200 watts at 48 volts. That would allow for a total of 8 400 watt panels per solar charge controller. We could do 2 strings of 4 panels in series, so we stay within our voltage, and multiple solar charge controllers are also an option if you wanted to run a lot of different strings. When solar panels are in series and one of the panels is shaded, it can affect the entire series string. If you have a couple of series strings of panels in parallel and one of the panels is shaded, only that series string in which that shaded panel is involved will be affected. Other series strings that are not shaded but are in parallel with your shaded one will still produce normally because it's not affected by the shaded panel. If certain panels are affected by shading, so whether by shade, clouds, whatever, only that portion of the total array that is in that specific series string would be affected, but not necessarily any of the other series strings that are in parallel with the shaded string. Follow that. Let's look at some examples. This setup features a 24 volt battery pack with 2 12 volt batteries in series. They are charged by 1600 watts of solar. The solar array is 2 series strings of 4 panels that are in parallel. A basic rule of thumb for smaller systems is that the total watts of the solar array divided by the voltage of the battery pack will give you the output current of the charge controller. For example, the 800 watt solar array divided by 24 volt battery pack equals 33 amps. The rating of the solar charge controller should be at least 40 amps. Note that the battery pack to the solar charge controller should be switched and fused and is also polarity specific. And your solar charge controller will be labeled with the solar input positive and negative and the battery input positive and negative. The solar panels to solar charge controller should be switched and fused also and polarity specific, like I just said. Also, always connect the power from the battery pack to the solar charge controller before connecting the power from the solar panel to the solar charge controller. Very important. Notice that there are fuses for each string. There are the 15 amp fuses in the diagram, as well as you can see a 30 amp fuse. Now you could use one 30 amp fuse in place of the 2 15 amp fuses. However, I recommend that solar strings be fused individually. So forget about the 30 amp fuse and use the 2 15s. This setup features a 48 volt battery pack with 2 solar arrays and 2 solar charge controllers in parallel. There are 2 separate solar arrays, each with 2 series strings of 4 panels that are in parallel. Each solar charge controller is connected to 3200 watts of solar. This means that 2 60 amp solar charge controllers could be used. The size of the wire from the solar array to the solar charge controller will depend on the maximum output capacity of the array and the distance between the solar array and the solar charge controller. That's why the closer your panels are to the solar charge controller, the better, because you have less line losses and it'll save you money because you can get by with smaller gauge wire. Notice that the battery pack is switched as well as the solar arrays. That way you can disconnect the battery pack from everything and you can shut off the solar arrays. And there's lots of reasons why you may want to do that. Like I said, initially you want to always connect the power from the battery pack to the solar charge controller before connecting the power from the solar panel to the solar charge controller. Also notice that the solar panels were fused as well as the charge controller. Fuses are your friend. A solar combiner is a box that combines, organizes, and houses solar strings. It takes the output of several solar panels and combines them into one line before they go on to the controller. Most solar charge controllers have a display and/or app that allows for all kinds of information, both in real time and historical information. If you have any questions or comments regarding solar charge controllers, please leave them in the comments below. I thank you for watching, and if you would, please like and subscribe. Hope to see you next time.